this video, I want to do an example problem related to relative motion. So the setup of this problem is that we have an elevator shaft, and in that elevator shaft there's an elevator platform that is moving upwards at a velocity of 2 meters per second. And while this is occurring and the elevator platform is located at 5 meters, someone sticks their arm into the elevator shaft with a ball, probably not recommended, and tosses that ball into the air and gives it an initial velocity of 18 meters per second. So with that setup, we want to determine when and where the ball will hit the platform and the velocity that the ball will hit the platform with. So to begin, we need to start thinking about what is the setup, what kind of things do we know about this problem. Well, we kind of have two things going on at the same time. We have the ball doing something, and we have the platform doing something. And one of the first places that I would suggest to start thinking about this problem is what sort of scenario do we have at play? And something that I've talked about in a previous video is the idea that we have kind of special cases that sometimes apply to these sorts of problems. And in this case, I would say that for the ball, we have one of those special cases in which we have constantly accelerating motion. And the reason we have constant acceleration is because the ball is being acted on only by gravity. After it's given an initial velocity, only gravity is doing anything to it at that point. For the platform, the problem statement basically said that the platform is moving up at 2 meters per second, and if we assume that to be steady and not changing, then the platform is under a constant velocity condition. So that gives us some information that we can work with. All right, so for constant acceleration, we have a couple of equations that we can make use of, one for velocity and one for position. So I'm going to go ahead and write the velocity equation, giving a subscript of b to indicate that I'm talking about the ball in this case. And our equation is v naught plus at. So again, working from our problem statement, we can see that we know some things and we don't know some other things. We do know that the velocity, the initial velocity of the ball is 18 meters per second. And we know that the acceleration is going to be the acceleration of gravity, and I'm giving it a negative sign for the downward direction. Time, we don't know, and VB, which I've left off, that VB is a function of t. VB we don't know because we haven't specified anything about when the time is that we're looking at. Next, we have the position equation, which is of the form y naught plus v naught t plus 1/2 at squared. And we have some things that are the same. We still know v naught, which is 18. We still know acceleration. And we know the initial position of the ball, which is 12. Great, so putting these numbers to these, we end up with VB equals 18 minus 9.81 t, and YB equals 12 plus 18t plus, I'll write that instead as minus 4.9 t squared. And that's what we know about the ball. Next, we'll move on to the platform. And under constant velocity condition, well, we know what the velocity is, right? V sub p for platform equals 2 meters per second. Yp, which is equal to y naught plus vt. And in this case, again, I can plug in what I know. I know that my initial position is 5 and my velocity is 2. So this gives me 5 plus 2t. So ultimately, the first part that we're looking here is when and where this collision between the ball and the platform will occur. And based on the fact that we're looking for a collision, the condition that we have under that assumption of these two things are colliding is that they must have the same position. So we can set yb equal to yp, which gives us those two equations, 12 plus 18t minus 4.9t squared is equal to 5 plus 2t. Now, we can solve for t in this problem because it's the only variable that shows up. So I'm going to go ahead and subtract over the 5. I'm going to subtract over the 2t. Set this equal to 0. And now I'm going to apply my quadratic formula. So I find that t is equal to negative 16 plus or minus square root 16 squared minus 4 times negative 4.9 times 7, all divided by 2 times negative 4.9. And if I run all this through my calculator, I'm going to get two answers. In this case, only the positive answer would make sense, so I'm going to get 3.653 seconds. And that tells me the time at which this collision is likely to occur. Now, that's one part of my answer. The other part of the answer is where. So where are the ball and the platform when this happens? Well, of course, again, that's related to position. And I can substitute this time into either of the position equations that I have. I might as well pick the easier one to work with. So I'll use the platform equation and say it's equal to 5 plus 2 times 3.653. And in that case, I'm going to get 12.3 meters. So coming up here to my picture, I can see that I tossed the ball up in the air, it went up, it started to come back down, and met the platform at 12.3 meters, so that's basically just above where the ball started. So the ball traveled up in the air, came back down, and the platform had basically come up to meet it, nearly at that same location. The next question asks, or the next part of the question is, what is the velocity of the ball when it hits the platform, or the velocity that it strikes the platform with? I need to be careful with my wording there because the absolute velocity of the ball and the velocity with which it strikes the platform are two slightly different things. If I'm looking for the velocity with which the ball hits the platform, I kind of want to take into account both the fact that the platform is moving and the fact that the ball is moving. So in this case, I'm looking for the relative velocity of the ball with respect to the platform because I'm referencing a moving frame in this case. And if we recall for relative velocity, if I write ball slash p or b slash p for ball relative to platform, the rest of the equation is velocity of the ball minus velocity of the platform. So I can go ahead and substitute in what I know from that. First, the velocity of the ball is 18 minus 9.81 t, and the velocity of the platform is a flat 2 meters per second. And this equation I can take and substitute my time because, again, that's when the collision occurs. So I'm going to take that time and plug it in there. So I'm going to get 18 minus 9.81 times 3.653 minus 2. And this comes out to be negative 19.84 meters per second. Great. So what that tells me is that the ball strikes the platform with a velocity of 19.84 meters per second, and it's negative because it's coming in the downward direction while the platform is moving positively in the upward direction. So if I was trying to figure out, how this is all occurring, I would need to take into account that negative sign and the directionality of all that. All right, thank you very much.